Yeah, so again, my name is Matthew Rocklin. I do a lot of open source work, and I found that, so I like to increase access to open source for other developers. I think that there's a lot of good things about that. Particularly, this is also in the education track. So this talk is going to be sort of half about education and open source and how that's actually a very valuable thing. Most of the talks about education have been, I teach a class, here's my experience. So I help out with an open source project, here's my experience. And I want to sort of motivate that. I also want to make this discussion that as open source projects grow and they become larger, both in community and in scale, they become harder to access. They become harder for developers to jump in. And so how do we maintain a low bar as we become more important, as we become successful? There's some interesting, there's really some interesting sociology in that. So taking control, what do I mean by that? So control flow is an element of programming. It's code that you write that determines which other code gets run. So do I run this function? Do I run that function? Do I run this code block? Do I run this code block? So things like if, or while, or for, or methods in classes, that's all control flow. It determines what code gets run. So that's what I mean by taking control. And my claim, my thesis, sort of a funny thing is that we should remove control from scientists and mathematician users. We should actually do automated control. So let them write small bits of code, but have some centralized system that determines which pieces of their code get run. I'll talk a little bit about SymPy and how we do that, how I would like to do that in SymPy, lessons from that. So again, we have this. So while the scale of projects is increasing, I would claim that the median programmer is decreasing in skill. And that's not because programmers are getting worse, it's just because we're getting lots of new programmers. And they might be really good at mathematics, really good at science, but they tend not to be traditionally trained in computer science. And so how do we leverage them? I work on SymPy. SymPy is a computer algebra system, and we actually really need those mathematical users. It's hard to find people who are both simultaneously trained in mathematics and in sort of compiler mechanisms that SymPy might use. So today, the first half of the talk is going to be about SymPy and not the actual project, but just sort of the developer demographics within that. In the second half of the talk, I'm going to talk about sort of things from funny languages that I've tried to port over to Python in an attempt to solve what I think is a serious problem. Okay, so what is SymPy? SymPy is a computer algebra system, which means that you type in math and you get out math. So we manipulate mathematical expressions as data structures in code. So mathematical expression is sort of a tree in code. And we might perform mathematical operations which are actually just manipulating that tree. So here we're grabbing the radial wave function of the carbon atom, I think, and there's some expression. So someone needs to know physics to write this code into SymPy. We take the derivative of that. Someone needs to know some mathematics in order to write this code into SymPy. SymPy does all these things. And then there's a lot of shared structure in that expression, and so we can simplify that expression down to some simpler expression. And this is really a large tree manipulation. Someone needs to know how to manipulate trees in order to do that. So I'm going to think that's sort of a computer science problem. Okay. So again, internally, SymPy represents expressions as these trees. This is there's a lot of shared structure in here, there's a lot of repeated arrows, and when you run some commands on it, it becomes simpler. So this is sort of the problem, I think, is that we need to know both mathematics and we need to know how to manipulate data structures efficiently. And it's hard to find people who know both. Okay. So who actually contributes to SymPy? And so I'm talking about Google Summer of Code a bit, and we take applicants over the summer to work with us for 10 weeks. And this is like this is a paraphrasing of an email that we got by actually a very bright guy. So I'd like to contribute some work in quantum field theory or the mathematics behind quantum field theory, but I only started programming a few weeks ago. Can I help? And the answer is that we actually need this guy, right? There's no one who knows how to program very well who also knows quantum field theory. Like there's maybe 2 people like that in the world, right? So we need this guy. How? But he doesn't understand all of the nuts and bolts of the internal core of SymPy. So how do we expose SymPy to him in a way that he can meaningfully contribute? And there's a good education that happens there. We get something out of it. He gets something out of it. It's a good experience all around. So here's some contributors. This is the top K contributors. I've noted people's affiliations when I knew them, if they were a student at the time which they were contributing. I've also noted which ones of them were Google Summer of Code students. That's this GSOC bit. And so you can see that lots of the top contributors, myself included, came in as a Google Summer of Code student. Aaron Mura is here. He's the current lead. Andrei Chertik started the project. Brian Granger's there at the bottom. He was faculty. He doesn't really count as education. But there's other folks that are hanging around. And this is just the top K. So there's lots more. Google Summer of Code is a great organization. Google funds open source projects to fund students at the undergraduate and graduate level, around 5,000 per summer for 10 weeks. They get to work from home, they get to interact with the community. We get students from undergraduates, from graduates. We get high school students that are actually often very successful. All latitudes and longitudes. I'm co-mentoring a student in India with a guy in Moscow right now, so it's a very global activity. They have a good time, they learn Git, they learn GitHub, they learn how to interact with the community. They get, ideally lots of code review. I'm pretty bad at that, actually. They also do real work. Like SymPy that you use today would not be half as awesome as it would be otherwise without these students. Lots of SymPys built by student workers. And we keep about one a year. So I'm one of the one a year. Google Summer of Code, it's the 10th anniversary this year. They don't only fund SymPy, they fund lots of open source organizations. Lots of organizations in this room, I assume. So it's sort of a thing. That's an educational bit. So it's interesting when you look at projects and look at the committers to that project and how many commits they've done. Thank you for Aaron for doing these plots, by the way. So on this plot, I'm showing the number of people that have committed 1,000 commits, 2,000 commits, et cetera. So we're sorting all of the committers by the number of commits, and we're plotting that as a line. And what's kind of interesting is you actually see this, so you see it's a log scale, so you see there's always a few hero committers, just really awesome committers in every project. And then there's sort of lots of one or two committers. Okay. But there's interesting things to think about. There's only really a few heroes. In no project that I've listed here, you never get 10 heroic programmers. There's always sort of 3-5 people who work on everything. And it trails off pretty quickly. SymPy is this weird exception. We actually have, many contributors who contribute many tens of commits. This is in the last year. If you look at this data for all time, you get a plot like this. And this isn't saying that SymPy is a bigger project. I mean, most of the commits are actually in the left side of the plot. We're just saying that we have a much broader base that contributes on SymPy. And that broader base is, again, not all programmers. A lot of them are mathematicians, a lot of them are scientists. They don't all know how to program particularly amazingly. And so that provides a lot of strain onto the code base. On the one hand, we really want to welcome people into the community and accept their contributions so they feel good and we want to teach them things. On the other hand, we need to keep the code base clean so that future generations won't be entirely frustrated by the process. So there's this real tension there about accepting code that should be either very high quality or welcoming people into the community. That's, I think, a tension that lots of people face, and that as we have more domain science, but not necessarily computer science contributors, that's, I think, a tension that a lot of us will feel more. I think SymPy might be like on the leading edge of that, but I think other people will also experience that. As you need a sociologist to work in pandas, or that might come up, how do you actually engage that person? Okay. So again, I think we need to sort of think about open source. A lot of us, I think, in this room were taught by each other on how to program and how to manipulate the coding ecosystem, and we should sort of recognize that. I also want people to start thinking about developer demographics and how they're changing as computation is sort of spreading out to the non-computer science fields, even the non-STEM fields. Okay. So the second part of my talk, so that was the education part and sort of the motivation part. I think that's something you should think about on your own. The second part of the talk is how do we build systems that allow people to make small contributions and hook those small contributions into a larger system. Most of this comes from sort of esoteric languages, or actually quite normal languages sometimes. So this is the wacky part of my talk. My sort of hobby is looking at weird programming languages, finding things in there that I think are useful to general programming languages, and then trying to implement them in a way that is not wacky. So lots of functional programmers, lots of Haskell people talk about things in a way that's incomprehensible to most. I'm going to try to talk about them in a way that's, I think, very accessible. The most accessible of those is a project that I want to sell to you for free called Multiple Dispatch. There's this idea of polymorphism, that we have a function that operates differently on different inputs. So we're all used to this concept. I'm just giving it a name called polymorphism. So the stir function, for example, acts differently if I give it a float if I go to a NumPy array, that function works very differently. So we build that function all together with a dispatch system. In this case, object-oriented methods. Okay. So objects, methods, dispatch on the first input, self. And if self is a float, we use float.stir. If self is an ND array, we use NDArray.stir. If self is a foo, we use foo.stir. So we've all collectively defined this stir operation democratically, right? I wrote stir on my classes, you wrote stir on your classes. Together we all made stir. But this breaks down very quickly when you have more than one input. For example, add takes both self and other. And so if you look at lots of add methods, they dispatch on other inside. You get all this sort of is-instance checking. This happens in SymPy in a terrible way. So here's the add.flatten method. And you see if it's a number, we do something. If it's complex infinity, we do something else. If it's an add, we do something. If it's a mold, we do something. And this code quickly becomes broke. No one can really contribute to it. I am scared as heck to contribute to this code. And so a novice contributor has really no chance. And if they want to add something that works with add, they're sort of forced to go into this piece of code, and it's a challenge. So there's this library, multiple dispatch. I made it after I was playing with Julia for a while. People who were in the Julia tutorial by David Sanders might have sort of learned about multiple dispatch a bit. It's a nice idea. It's also an old idea. C++ has it, Java has it. But so the idea is you can decorate your functions with the input types. And then there's a separate system which will figure out which function you actually meant to use given the inputs that you had. So here I define add on ints and on objects. On objects, we turn them into strings and concatenate them, kind of like a JavaScript add. And we can see that we use it in two ways, and it works in the right way. Okay, so here's multiple dispatch. Jeremiah Lowen, I got a pull request from him with actually using Python 3 annotations. Python 3 actually has native support to annotate input arguments. It doesn't do the dispatching mechanism. You still need to annotate the function with dispatch. But there's, people are thinking about this sort of application. So my use case for this is into. So the idea is you have one container type, like a list or a NumPy array or a data frame or a PyTables table or a Spark resilient distributed data structure. You want to turn it into something else. You want to turn a pandas data frame into a NumPy structured array. Okay, so in all these classes, we have to NumPy array from NumPy array, to CSV from CSV. We've effectively done a double dispatch system on our own. Into just collects all of those things into one global interface. And so if I know, say, sparse matrices really well, I can write down how to turn NumPy arrays into sparse matrices, and that just gets registered with the into operator. Okay. And so here we're turning a list into a tuple, an array into a list, a data frame into a structured array, and a NumPy array into a sparse matrix. The API was the same. And again, it's sort of nice because one person can write one implementation of this without having to touch all the other code. So I think my goal is to make lots of small functions, okay, and then have people have an automated system combine those together. So I think that this is more accessible to junior students, even a large project. We've broken up a big project, a big task into lots of small things. People can become an expert in their little small thing and contribute meaningfully. So again, we want to sort of collect meaningful contributions. Okay. Yeah, so I'm going to skip some of this. So strategies is a module that's sort of very loosely influenced by this language Stratego, which is a strange language. But so there's this idea called map. Okay, so normally we take a list, we add a bunch of elements to that list with adding some function, and we concatenate the results. We get the results. And this function map is this hardware function that does that same control pattern. So remember, for is sort of this control piece, and map sort of encapsulates this idea of this control piece. Now in practice, you use list comprehensions, but I want to give you the idea that we can write functions that capture common control mechanisms. Okay, so that's an idea. I'm going to have to skip some of this because I'm low on time. So like exhaustive application is something. You want to keep applying this function many, many times until I reach a fixed point. Okay. So keep applying this function until it doesn't do any good, then just give me the result. That's a common thing that you do in your code. You don't realize that you do it. You don't call it the exhaustive or repeated or fixed point pattern, but it's a common pattern that you do. Let's see, what else did I have here? Oh, right, so here I have this so I'm going to I'll give you the example first. We're going to build trigonometric simplification. This is an application in SymPy. Take a trigonometric expression like sine squared x plus cosine squared x and produce 1. So how do we actually do that in SymPy? What's our mechanism to accomplish that transformation? And what we're going to do is we're going to write lots of little small functions, and we're going to compose them explicitly into some sort of tree. So here I've got a couple small functions, double and square, and I'm going to make a new function, which is either going to double or square the input, and then call string. So wherever you see a list, that's a choice. I'm going to choose one of those two options. Whenever you see a tuple, that's a chain. I'm going to do this one, and this one, and this one. Okay? And so I'm going to choose whichever, I'm going to give it an input. I'm going to greedily search for the minimum output I could have gotten. So if I give it 0.5, it says, oh, hey, squaring, that's better. So I'm going to call square and then stir. If I give it 10, oh, doubling is smaller. So I'm going to call double then stir. Okay. So this is a way to write lots of little small functions, and then also explicitly write down a set of options, a set of paths that one might take through a program. Usually this would be lots of if statements, lots of checks, testing some objective function, seeing which one's best, choosing that route, going on. You'd be explicitly writing in greedy search all the time. We've instead written down greedy search in a totally separate way. So again, here's a small little function that does one small, simple trigonometric simplification. It turns cosecants and secants into 1 over cos and 1 over sine. So this is a transformation that I think everyone in this room should be comfortable with. And a high schooler might also be comfortable with this transformation. They could write this transformation. We write down lots of them. So here's lots of little transformations. These are all functions. They're all separately doc tested. They're separately tested. This is sort of, again, work that anybody could do. We then explicitly write them down into an explicit set of options that one might take. Okay, so this is actually from a paper by Fu. And he writes down this, he sort of prescribes this mechanism by which you can compose all of these little small transformations to do robust trigonometric simplification. Once you have this sort of tree, this is all sort of crazy stuff. If you don't get it, that's fine. I'll show you magic in a bit. But then we call this sort of greedy search function on this tree. And so the greediness, the search part, and the trig part are totally separate. And so a computer scientist can write the greedy part, the searching part, and the high school student could write all the trig stuff. And so what we get, so we can call trig simp on a simple expression, and we can even pass in objective function that we want to minimize. So we want to minimize the length of the string of the output, and indeed we get out 1. We could also try to maximize the length of the string of the output. Sine squared plus cosine squared. So that's kind of neat. Here's a more complex expression, and we can do wacky things like please give me as many sines as you can in that expression. This work is mostly done by Chris Smith. It's in SymPy. SymPy runs on this. But again, I want to sort of come back to this idea that we can break up the hard problems that we do into lots of small pieces, and then some automated system that tries to connect those pieces together. Maybe that's a more scalable way of developing. It's a more scalable way of including a community. So there's sort of magic in the programming languages stuff here that is weird and wacky, but it's, in general, when you think about how can I take my problem and actually think about what pieces are best for computer scientists, what pieces are best for domain scientists, and how can I actually architect my software system so that I can engage both of those groups of developers. So I'm not depending on people who know both things simultaneously. Very quickly, I threw this together, I think, last Friday, based on other things I've been working on for a while. But unification is a form of pattern matching. Who here knows what unification is? Just curious? Yeah, that's what I thought. Yeah, okay, so there's actually no hands. Aaron, you gotta raise your hand. Yeah, there's a hand back there. Thank you, sir. Thank you. You're making me happy. So unification is pattern matching. So 1 matches to 1, 1 does not match to 2. If I have a wildcard x, then x can match to 1. And in this case, x comma x can match to 1 comma 1. But x comma x cannot match to 1 comma 2. So some languages support pattern matching in a rich way. It's really part of the language. Here's a more complex example. We've got a little, response, HTTP response. with a status, and we sort of want to drill down and get some text, and we can use these wildcards to pull out that data in a very declarative way. We're sort of writing down what we want, and we get to pull it out. Okay, so why do we care? I'm running low on time. Here we go. So here's a more complex example. Is this legible? Can people see this? So here's a more complex example. Here's sort of a Flask-like application that takes lots of dictionaries, and if the input is an OK status and it has credit key and amount, we're going to add that amount to someone's name, their balance. If it's debit and some amount, we're going to debit that amount. And if it's a 404, then we're just going to print out bad message. And so this code runs, it works. It's code that's very declarative. It's code that removes a hurdle in the way of a lot of developers of traversing these data structures. So this is unification. Again, a little small project. It's sort of fun. Okay, so that's the end of my wacky programming examples. I want to bring you back to this sort of idea that we should be thinking explicitly about our developer base and what they can and cannot do. In my personal experience, I've found that weak developers but strong domain scientists can write small bits of code very, very well using their expertise, but they tend not to be able to architect large systems that determine which pieces of code should be run. And so I have sort of ways in which I've tried to do that in the past. Of the three that I've shown you, I recommend multiple dispatch. That's actually ready to go. People should be using it. But even if you don't want to use my things, think about this problem. Think about the demographic problem. Okay? So that's my talk. Thank you for your attention.